Okay, now we're going to attack one that's a little bit larger, and we're going to both maximize and minimize this one because it's actually going to be a bounded region. Now I've actually already done this in a previous example, but we'll go through it again here. So if you have the first inequality, 2x1 plus 4x2 equals 24, so the intercepts for that would be if x1 is 0, x2 would be 6, and if x2 is 0, x1 would be 12. So that would go through 0, 6, and 12, 0. Now, so actually I don't have room to list those. So let me see which one's the lowest y. Let's see, the y values are going to be at 6, 7, and 10. So let me see if I can do it this way. Let me see, I'll try to get the points on here for you. Let me pause the video while I do this. Okay, so that first boundary went through 0, 6, which would be about right here. And it also went through 12, 0, which is way out here. So when I drew that line, it gave me this brown or dark colored line, and when I test 0, 0 for that one, I got a true statement. So I actually have to shade this side of that line. I'm just going to draw one arrow. So I have to shade below that line. And then the next one, 3x1 plus 3x2 is less than or equal to 21. That goes through 0, 7, and 7, 0. And so 0, 7 would be about right here. And then follow it down here to 7, 0 right here. And that would, so I graphed that one in green. So if you see that green line. And so what you have to do now is if you test 0, 0 for that one, you get a true statement. So we would actually shade below the green line. So we would shade that side of that line. So now, if you think about it right now, let me see if I can draw out what I would have so far if we stay in the first quadrant. If we stay in the first quadrant, we would be bounded by this line. Then the boundary would change to the green line until we got down here to the x-axis, and then it would be bounded by the x-axis and then back up again. Okay, but we've still got one more inequality, and so this inequality, 4x1 plus 2x2 is greater than or equal to 20. It's going to go through 0, 10, which is way up here, and 5, 0, which is down here. So if I draw through that line, now when I test 0, 0 for that boundary, I actually get a false statement, so I have to shade this side of that line. So now if you think about it, once you shade the upper region for the blue line and the lower region for the other two lines, the solution is just going to give you this triangle right here. So rather than let me draw it, let me just kind of show you. You're just going to get this triangle that goes from here to here and then up to where the blue and the green line intersect, and then back down to here. So that's going to give you this triangular region right here. Now, how do I know this is 3, 4? I know it's 3, 4 because I actually had to find where the green and the blue line intersect, and let's see if I can show you which pair that is. Let's see, the green line goes through 0, 7, so I had to solve the system for this equation, and then the other one goes through 0, 10, so that would be this one. So I actually had to solve this system of equations here to get that point of intersection, which is 3, 4. And you can check it real quick. 3 times 3 plus 3 times 4 is 21, and then 4 times 3 plus 2 times 4 is 20. So you know that 3, 4 actually works. Now, notice these other intersections are not in the region, like where these two lines intersect, where the brown and the blue line intersect is not in the region. Where the brown and the green line intersect is not in the region. So even though we have lots of points identified here, the only points that are corner points in the region are these three values that are on this triangle: 5, 0, 7, 0, and 3, 4. So if those are the corner points, then what did I want to do? I wanted to maximize and minimize this. And since it's a bounded region, remember it's a bounded region because I can enclose it. So since it's a bounded region, I will have both a maximum and a minimum. So let's plug 5, 0 into the function, and that'll give me 15. Let's plug 3, 4 in, and that'll give me 9 plus 16, which is 25. And let's plug 7, 0 in, which gives me 21. Now, notice that the smallest value I got was 15, so the minimum was z equal 15 at the point 5, 0. The largest value I got was 25, so the maximum is z equal 25 at the point 3, 4. And so that's the solution there for this problem. So again, on that one, we can actually maximize and minimize it since it's a bounded region. Now, here's a couple more problems that you can pause the video and write them down and work on them for practice. Both of these ask you to both maximize and minimize the given function. Now, one thing that you might find interesting on this one, is that you can only have one maximum or minimum, but the maximum and/or minimum could occur at two different values. So this graph actually has two minimums, it only has one minimum of 160, but it occurs at two different points. So even though it occurs at two different points, you still only have one minimum at 160, but you still should go ahead and list both points where it occurs. All right. So in the next video, I'll set up 2 or 3 word problems for you and solve them.